Hello, everybody. I'm recording this ACC tutorial from my home in Irvine, California. I want to begin by thanking Professor Vidyasagar for organizing this session, and I wish it was in person instead of this video meeting. At any rate, I'm delighted to be part of this tutorial, and what I will do is to talk about a concept called cognitive cyber-physical systems, which brings together cognitive neuroscience, machine learning, and control. The outline of my talk is I'll provide some context and vision for what we are talking about, then the concept of cognitive cyber-physical systems, which is the main body of the talk, some technical directions, and just a brief comment on our recent work. So really, for me, the motivation for this thinking goes all the way back to the founding of our field and to Norbert Wiener, one of the visionaries of the field, who created cybernetics. And on the right-hand side, you see cover of his book, Cybernetics on Control and Communication in the Machine, in the Animal and the Machine. And also I want to reference Macy conferences, which was a series of conferences held in the mid-40s. And there is a link to that. In fact, it's a good place to comment that throughout the presentation, there are hyperlinks that you can click on and get much more information about what I'm talking about. So there was a series of conferences that's called Macy conferences that brought together people from control, communication, information theory, which were just beginning at the time, and also from neuroscience, cognitive science, psychology, and many, many different fields, computing. And in fact, all the leading thinkers of that time were involved in these Macy conferences, which forms a very rich background for bringing together control with many other fields. And so one way to think about a question that might motivate us to think for ourselves is, if these pioneers were around, how would they envision future of cyber-physical systems? So a quick word on cyber-physical systems. It's something that you probably all know, but just to recap, it's a concept that, in fact, NSF played a large role in, along with many other agencies like Department of Defense and Department of Transportation and so forth. And intellectually, at its core, it consists of several fundamental fields, such as control, communications, networking, real-time systems, security, and safety verification, and so forth. And then it has a number of application domains that are depicted on the outer circle. And 4 of those are shown in a little bit more depth on the right-hand side. So for example, transportation, which would include smart transportation, energy efficiency, energy and industrial automation, building energy efficiency, IoT, things like that. And then healthcare and biomedical, ranging all the way from devices to running a hospital, where cyber-physical systems can play a big role. And then in critical infrastructure, things like smart grid, smart transportation, and many, many different application domains. If you look at what's happening now, is we see everywhere this idea of smart something. And very simple conceptual way of thinking about it is that we bring together sensors, communications, Internet of Things, automation, alongside data analytics, machine learning, AI, controls and decisions, and then implement these on software architectures with cybersecurity in a variety of computing platforms, from desktop, from mainstream computing to cloud and edge computing. And X can be any application domain. So you can think about smart transportation, smart grid, smart healthcare, smart cities. They all fit in this general paradigm. And so these are aspirational examples: smart manufacturing, smart grid, and so forth. And then also autonomous systems, things like unmanned air vehicles, self-driving cars, autonomous robots, also fall into this general paradigm. In all of these, one point we are particularly interested in is that human behavior at the individual and group level is central to performance of these systems. So altogether do they bring about the benefits that people envision for them depends upon getting engineered systems to work with humans in various different ways. And all of that leads to the idea of smart cyber physical human systems. So how might we go about realizing these smart cyber physical human systems? For that, I want to introduce the concept of cognitive cyber physical systems. Before I do that, it's really a good place to bring in David Marr's 3 levels of analysis. And David Marr was a visionary researcher. He specialized in computer vision. And he proposed that any system which exhibits cognition or intelligence can be seen at 3 different levels. One is, what's the goal of the system? That is, can one describe function or goal in a computational framework? So what is the system supposed to do? So if you think of vision, you can say, okay, what is the system supposed to do, which is to take input data, sensory input data, and turn it into information about the visual scene that you might be seeing. Once you have the computational goal, then you can think about what are the algorithms and on what architectures those algorithms are implemented. So by here architecture, I mean really information architecture, not physical hardware architecture, but architecture of information and the algorithms that run on that architecture. That would be second level of analysis. And then finally, how is it implemented? So if you instantiate this for the human brain, the implementation would be our brain, neurons and their connections to each other. That would be the implementation level. Algorithms and architectures would be different algorithms that the brain employs to take in all the sensory data that it gets through our eyes, through our ears, and other parts of our body, and it converts it into information and cognition. So that's Marr's way of Marr's sort of 3 levels of analysis. And the way it connects to cognitive cyber-physical systems is that the upper 2 levels can remain the same as in our brain, for example. And the third level will be computer chips, software, and also the physical infrastructure, say the electric grid or the transportation system or the robot or the airplane. So at the implementation level, it is physical hardware and computer hardware, but the other 2 levels can remain very similar. I now can turn to definition of cognition. And in fact, cognitive science went through a revolution, cognitive psychology in particular, and Ulrich Neisser was one of the major participants in that revolution. In 1967, he proposed a definition for cognition as all processes by which sensory input is transformed, reduced, stored, recovered, and used. And he called that cognition. Now, one has to recognize that in case of our human brain, there is a very, very important role of built-in capacity that comes because of genetics and evolution. So for example, human brain has an inbuilt capacity for understanding symmetry or understanding intuitive physics. And all that is sort of built into our brain because of our evolutionary past. So there is this built-in capacity, and then we learn after our birth, and that turns into this whole thing called cognition. Some of the key cognitive functions are perception, attention, memory, reasoning, problem solving, and knowledge representation. I have referenced here a couple of major books where you can get a lot more detail. So using this definition of cognition, we can define cognitive CPS. So sort of our working definition, and it's a working definition. Why? Because I think we are at the very beginning of thinking along this line. And so I want us to be flexible in refining this definition. But for now, these are cyber physical systems that have cognitive functions and capabilities. Now, CPS can be explicitly designed to have these functions, or they can learn to possess these cognitive functions. And we can have both possibilities or combinations thereof. Third, the need for what cognitive functions you need and what capabilities you need will depend on the problem. So we don't want to say that we need to have everything in our cognitive CPS. Depends on the problem, we might need one or more of these cognitive functions or capabilities. Fourth thing, that we envision that this cognitive CPSs can learn from each other. So transfer learning, which is a concept in machine learning, is a simple example how one can learn, how one can transfer learning from one to another CPS. They can learn from humans if we design them right, and also form collaborative networks. So you can think of autonomous robots working together as a form of cognitive CPS that are working together. And our hypothesis is cognitive CPS will be better able to augment humans and lead to human flourishing. That is, if we build in these cognitive functions from the very beginning, then there is a chance that we will be able to design these systems that work well with humans, both as individuals and as groups. And in my humble opinion, cognitive CPS concept offers the most expansive and ambitious program for integrating advances in machine learning and AI with cyber physical human systems to create these smart systems. And I'm going to try and make this claim more concrete in the next few slides. It's at this point, we can turn to cognitive models. Now, this is a really very, very nice diagram that I've taken from a recent paper by Krixcourt and Douglas. And it talks about various different cognitive models in two dimensions. On the x-axis is biological fidelity. That is, how close is the cognitive model in terms of mirroring what we know about the brain. And on the y-axis is cognitive fidelity. That is, to what extent does the model reflect what we know about human cognition. So as extremes, you have Hodgkin-Huxley model, which is the model of a neuron. It's a differential equation model, very well known. In fact, they won the Nobel Prize for it. Extremely high biological fidelity. I mean, people believe that it really does describe how a neuron operates. It's been tested for 60, 70 years, if not longer, but really doesn't explain anything of the cognitive function. And IBM's Blue Brain project, which is a much larger scale version of that, also has high biological fidelity, but does not have much cognitive fidelity. On the y-axis, you have models such as cognitive, and I'll explain these cognitive models in the next few slides, which are very close to cognitive fidelity, but don't really connect to the neural substrate on which they are built. Deep neural networks sort of come between these two extremes. So they are abstracted versions of neural networks. They are not biologically realistic, but they do capture some aspects of network connections or recurrent deep neural networks, and so on and so forth. And the sort of aim of all these cognitive models is to move to the right and top so that you can explain more and more cognitive, higher and higher cognitive fidelity and higher biological fidelity, so that we get a really solid model for how our brain brings about these cognitive functions. Before I go further, I want to point to a debate that's been going on for, ever since AI started, pretty much, which is symbolic versus neural connectionist approaches. Like I said, it's a historical debate on human cognition and the brain. It's a key topic in cognitive science, in neuroscience, in machine learning, in psychology, in linguistics. And there are three major components. One are computational logic systems. Second is connections neural network models. Think deep neural networks as an example. And then models and tools for uncertainty, because in all of this, these systems have to deal with the fact that the world is very, very uncertain. And we human beings and our cyber physics systems operate in uncertain environments. So we need to have models and tools for uncertainty. From my point of view, really, we want to be pragmatic. We want to combine connectionist, logic, and probabilistic approaches to achieve desired systems and goals. There is a very nice survey paper that I've referenced here, and you can go and read it for a much more detailed description of this. Okay, so cognitive models. I'll describe what is available in the literature. The oldest cognitive models are what are called production systems. They go back to the work of Newell and Simon at Carnegie Mellon. And these are essentially logic systems. So they have if-then rules, logic, symbols, they have goals and sub-goals, and they have conflict resolution mechanisms. That is, if two goals conflict, what should you do? And there are examples of large systems that people have built along these called ACT, for example, ACT-R and SOAR, and those are again links that you can look at to understand these systems. So those are oldest forms of cognitive models. Then there is a whole series of models based on reinforcement learning, which is a lot closer to what we know in control. So reinforcement learning models have agents, can take actions, there is state of the system, and then there are rewards that the agent gets. You can include perception and motor modules in these to make them more biologically realistic. And then there are optimization approaches based on value, function-based RL or policy gradient-based RL. In case of neuroscience and cognitive science, there are three possible modes in which RL works for cognition. One is model-free, second is model-based, and third is episodic. That is, you remember an episode. And a great example of this is learning to ride a bicycle. It is believed that brain combines all these three modes in its functioning and in achieving cognition, but it's really not known how this combination occurs. And then the third class of cognitive models are what are called Bayesian probabilistic models. And again, those are links to papers where you can see a lot more detail about these different models. At this point, I want to talk about one particular Bayesian model called the free energy principles. It's really absolutely amazing idea. It's the most ambitious principle for brain function. Is due to a British neuroscientist called Preston, and I've linked the paper there. And the fundamental principle that he says the brain is designed to do is it seeks to minimize surprise. And in that sense, it is very, very similar to, or it evokes, at least to me, Kalman filtering type of sort of, minimizing the innovation. Then there is connected to Bayesian brain hypothesis, which says that the brain has an internal model which allows for computation of state estimate from sensory observation using Bayes rule. So you have some priors and you get observations and you compute posterior, and that's how you estimate the state of the environment through this internal model. Now you can extend this to, so that was passive version. Then there is an active version where the agent, and we do this all the time, agent chooses actions. And then the extension of this idea is agent chooses action policy to maximize information gain. So you choose to align your observation in a way to maximize information gain. Information gain is quantified using Kullback-Leibler divergence or relative entropy. What Friston says is that the brain seems to operate to minimize expected free energy under future observations and future states. That is, it's not just the current state, but it also has an estimate of future observation and future states which are stochastic. And it actually minimizes a lower bound called variational free energy. And this concept has deep connections to statistical mechanics, to predictive coding, to risk-sensitive control. And it goes all the way back to people like Ross Ashby, who were part of the Macy conferences. So this whole thing comes together in just beautiful ways. So now I've sort of explained these different cognitive models. Let's look at these different cognitive functions in machine learning and in CPS. So let's begin with perception, which is like the most fundamental cognitive function that we possess. Think, hear, vision, and auditory system. And deep learning is truly revolutionizing perception. So in fact, you can argue that the biggest advances in deep learning have to do with how it has affected computer vision and speech processing and things like that. In these deep learning system, compositionality is built in, which gives them a tremendous advantage. And we have had very impressive progress in computer vision, speech recognition, language translation. And some of the key architectures are CNNs, convolutional neural networks, and long short-term memory, the recurrent neural networks. These are cognitive models, and they are being used for advancing perception. Now, perception in CPS, one can imagine CPS with multiple distributed sources of sensed information. So that's really a central element of a CPS. And so we can immediately leverage deep learning advances and integrate these sensors into our cyber physical systems. Prior knowledge plays a very, very large role in cognitive theories of perception. Without prior knowledge, really, we couldn't do the kinds of things that we do. So in all the man-made systems, we are going to need to integrate prior knowledge. And so one sort of approach that people are working on are neural network techniques that could be combined with relational prior knowledge for improved context awareness for sensor-rich CPS. In fact, there are lots of really simple examples that show that if you miss the context, you make very bad inference and very bad decisions. And there are potential tools and techniques for relational priors. So for example, you can have a neural network with symbolic front end with priors to learn the symbolic front end. And then there are graph networks. And both of these can potentially be applied in cyber physical systems. Next, I want to turn to attention. So attention has been a major focus, particularly in vision, and it's for human vision. In fact, one of the key things that we do is we know where to pay attention. And we need robots to do the same thing. We need self-driving cars to do the same thing. So it's been a big focus of, attention has been a big focus for cognitive modeling. So there are computational models. There are many different models historically in the last 30, 40 years. There is the feature integration theory, guided search model, code theory of visual attention, signal detection theory. Each of the blue bullet is a link to a paper where you can learn more about these models. There is a whole series of computational models, and I have linked a paper there where you can get a lot more mathematical detail. There is the ITIS model, which is in 3 dimensions, which looks at color, intensity, and orientation of the image. There are Bayesian models, not unlike what I talked about, for instance, free energy principle, which is far more general. There are Bayesian models of attention. There are decision theoretic models of attention, where you use decision theory. Information theory has been used for modeling attention. Graphical models, spectrum analysis models. So there is a rich literature on modeling of attention. Attention has played a big role in advancing machine learning. So in fact, it's key to focusing on most relevant information from multiple disparate sources of information. And in machine learning, they've been used for visual attention. They've been used for attention-based neural machine translation. In fact, it's been a big source of success in terms of automatic language translation systems. Neural image caption generation with visual attention. And in fact, that's the example where if you miss the context, you do a really bad job. So context is very important. And then in generative adversarial networks, self-attention has played a big role. And right-hand side, just a simple picture of how attention is used for machine translation. So how might we bring attention into CPS? So we think there are 2 possible levels of attention that we will need. One is first, selection and focus on a particular task. So as these cyber physical systems operate in the real world, we can imagine that they will need to choose and select what task needs to be done when. So that will be the first level of attention. And then once you've done the first level selection, then you need top-down search for relevant information. That is, to achieve that task, what do I need and what do I pay attention to? Attention for detecting changing conditions and context would be a very big role for attention in cyber physical systems. You can imagine this would happen in almost all applications. For fault detection and resilience, attention models that are hierarchical and programmable will be required. So there are some nice examples that are relevant that you can look at: self-attention models for deep learning, non-local neural networks for image recognition, and attentive meta learners. I will speak more about meta learning a little bit later, so let me not go there right now. Memory, that's the third cognitive function I want to talk about. So memory is certainly central to intelligent behavior. And in fact, if you think about Alzheimer's and dementia, once you lose memory, you sort of lose your personality, who you are. And so memory, certainly from a human cognition point of view, is central to intelligent behavior. There are multiple memory systems in human cognition. So there is the short-term memory, there is the long-term memory, there is episodic memory, that is remembering episodes. And then there's semantic memory, where you attach meaning to concepts and things of that nature. So if you think about memory, LSTM, which is a major architecture in machine learning, long short-term memory, is an excellent example of using memory in machine learning. Experience replay, which is another innovation in deep reinforcement learning, is another wonderful example where memory and reuse of memory plays a big role in performance of deep reinforcement learning. Then there is the idea of differentiable neural computer by Graves et al. I will explain that on the next slide, so let me not do that here. And then there is the idea of sparse distributed representations, because sparsity plays a big role in terms of memory. So there is a idea of Jeff Hawkins of hierarchical temporal memory. In fact, we have done some work on HTMs and their use in fault detection, and sparsity, which is another sparse representation. So sparsity plays a big role in memory. So this is differentiable neural computer. And really for this, I want to go back to the von Neumann model of computing, where you have the ALU, arithmetic logic unit, and then you have memory. In fact, this is sort of like a Turing machine type of idea, where there is computation unit, and then there is memory, and then you read and write to a tape, and that forms the most powerful computer that we know of. The idea here is you take a neural network as your computational unit with inputs and outputs, and then you have memory just like in Turing machine or von Neumann computer, and you have read and write heads. And Graves et al. Have proposed this architecture and have shown that this dynamic external memory can make a big difference in what you can achieve. And what's beautiful about their work is that the whole thing is differentiable. So you can learn parameters of the system by doing stochastic gradient descent, just like we know to do in deep learning. Another example of architecture is this MAC cell, memory, attention, and composition cell. It reminds me of LSTM cell, where so you have the cell in the blue, where you have inputs and outputs and recurrence relations. But then it also has a read-write to a memory cell. And this is recent work of Hudson and Manning, where they show that this memory, attention, composition cell, if you build networks from these types of cells, you can have some very interesting performance for all kinds of reasoning tasks. So how might we bring memory into CPS? So one example is episodic control. So episodic control is the idea of reenacting successful episodes from memory storage. So even though I have not used a bike in a long time, if I get a bike, my brain pulls in all the information about riding a bike from last time I rode or from my childhood and just reenacts that sequence. So episodic control has potential relevance for small data learning and control. So if you can do this, then you don't need a lot of data for training. And this has been tried. There is work going on now in this. Model-free episodic control by Blundell et al. Is a nice example of this. Model-free episodic control uses recorded experiences are used as value function estimators in an RL type of framework. There is neural episodic control, which combines deep learning model and lookup tables for action values. So there's another way of doing episodic control. And again, I've linked a paper there. And hierarchical episodic control. So episodes are used as options, and then you choose among options in a hierarchical setting. Okay, now I will, having explained three major cognitive functions, I don't have time to do the remaining, but there is, we can do a similar explanation of the remaining cognitive functions. There are major methodological challenges ahead. And here I've outlined four. First of all, we are going to need approaches for combining model-based and model-free techniques. If you think about control theory, most of our work is model-based. And a lot of work that's going on in machine learning and cognitive science and so forth is model-free. So how do we combine these? Approaches to combine hierarchical and distributed architectures and algorithms. We are not going to create one giant controller for these type of systems that we have in mind. They will be necessarily hierarchical, they will be distributed. So how do we do this? How do we reduce the need for large amounts of data that's common to machine learning? Because in autonomous systems and cyber physical systems, we are not going to have the luxury of collecting lots of data before we start. So things that can learn quickly, and examples would be like few shot learning, one shot learning would be useful. And then bringing meta learning paradigm. How can we learn to learn? So here are some initial thoughts on how I might do this. So Model-free ML-based approaches could be used for sensing, perception, and memory. And then we can use model-based approaches for planning, safety, and closing the loop, because that will allow us to do stability analysis and safety analysis. So this could be one approach to combining the two. And I think this is actually has tremendous potential. Then there is, of course, model predictive control and reinforcement learning is a nice way of combining model-free and model-based. So compute action sequence on the model via MPC and update the model via RL and supervised learning. And then guided policy search would be a third approach, which is robust local policies derived from local models, and local policies are used to guide a global policy, which could be model-free. Hierarchical control, hierarchical structures are absolutely necessary, as I mentioned earlier. In cognitive science literature, there is quite a bit of recent work on how hierarchies arise. And I've just linked one paper in that whole body of literature called Optimal Behavioral Hierarchy by Salve et al. Hierarchical control would be very important for sparse reward settings. So meta controller sets the immediate goal and subtask, and lower level controller achieves the goal. So hierarchical deep Q networks are an example of doing this. Hierarchical control also provides scalable methods for large state action spaces. And there are many papers that are doing this. So options framework, temporally extended sequences of actions to simplify the learning process. Feudal RL, higher level task is divided into hierarchy of tasks, and each task is then done by a controller. And a max Q framework is an extension of the classic Q learning in RL for the hierarchical setting. So each of those papers have much more detail about these ideas. Finally, meta learning. So meta learning is a paradigm for dealing with new environment based on learning to learn approach, and which is really central to human behavior. We learn how to learn. Classic, more or less classic by now example, learning from task properties, transfer learning from prior models. So if I learned in some setting, can I transfer that by changing just the last couple of layers of a neural network? It's called transfer learning. So that's an example of meta learning. We can think of meta learning for perception, so optimization-based approaches, metric-based few shot learning, learn a distance metric that's effective for classification from fewer examples. The example is Siamese neural networks. Again, you can look up that paper to see what the idea there is. And then attention-based meta learners, a hierarchy of temporal convolutions interspersed with attention layers. And really, for achieving the kind of autonomy and control under uncertainty, we are going to have these meta learning approaches built into our cyber physical systems. Finally, just a word about the work we have been doing. Like I said, we are at the very, very beginning of this thought process. So for me, it's like just an exploration that we have started. And here I want to show you what we have done in a very specific case. And the right-hand diagram is very familiar to every one of you, at least the upper part in a standard control diagram. And what we do is to augment an external working memory. So very much like the differentiable neural controller idea of Graves et al., we have brought into control, and we have applied it in an adaptive control setting. And we have also included attention layer in this work. So here are some papers that we have written. One of them came out at the CDC last year. And then my postdoc, Muthirayan, will give a talk on including attention in this at the ACC. With that, thank you very much.